All right, here is your last review, section 8 and 9 for genetics and biotechnology. So first, you're required to create a pedigree here based on this information. I'm going to bring up the pedigree. So let's remember our pedigree basics here. Here are your symbols. Okay. And your finished diagrams may look something like this, right? Showing multiple generations. And the filled in section shows the trait that we are looking for and looking for patterns within the family, which is what a genetic counselor would do. So for your practice pedigree, you had Chad and Veronica, and they mated and had 3 children. They had Brittany, Kristen, and Harry, and it was discovered that Harry had muscular dystrophy, so we're going to color that in, or we'll come back and color that in. We also know that Brittany married Larry and had Stefan and Stephanie. We also know that Stefan has muscular dystrophy. And then we also know that Larry's brother, Barry, has muscular dystrophy, but neither of their parents did. Okay? So that should be your complete pedigree. And when you color it in, it will look like this. This shows us our, this shows you who's been infected. Yeah? Now that we have the pedigree, we're going to go down to this one, DNA sequencing. Remember that there's a pairs here, so T, T, C, G, A, T. What's the complementary sequence? So we know that your hint here, T pairs with A. So here we've got A, A, T, T. So it's got to be one of these top 2. Then you've got C, G, A, T. We got G, C, so that's the same. And then we've got a U and an A, or a T and an A. So it's going to have to be this one. So letter B is your answer. You know you need to spin down reagents. So how would you put the tubes into the microcentrifuge? Color in the circles. And so if you've got 4 tubes, how would you do this? So you could do 2 here and 2 here, opposite, right? Or 1, 2, 3, 4. If you're going to show 5 tubes, the easiest would be to do 1, 2, 3 here, and on its opposite side, 1, 2, 3, and then you're going to draw in a balanced one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's 14 here. And so just knowing that, how would you divide it up? And so if you would take 6 away from 14, you've got 8 spaces. So you'd have 3 and then do 4 in a gap, and then 3 in a row, and 4 in a gap. Okay. Now, determining the amount of liquid in microcentrifuge tube 1 and A. How would you do that? Well, you add in 8 microliters plus 10 microliters plus another 6. And then your total amount here is going to be 24 microliters, right? You're simply adding those together. And then if you got 7 and 10 is 17 plus 5 means you're going to have 22 microliters, right? So here you have 2 tubes with different amounts of microliters in there. All right, now fill out this so it's correct. If you're using a P1000 and it says 030, that's going to be how many microliters? 300. If you're using a P20 and it says 125, that's going to be 12.5. And if you have 650 microliters to pipette, you're definitely going to be using 1,000. And you would write it with a 6, 5, 0 in order to look at me, I'm wrong. You would put 6, 5, 0, 6, 5 for that. And then if you are going to do 50 microliters, you would be using the 200 And that would be 0, 5, 0. Yeah? All right, there's your micropipettes. In order to examine DNA, it's a 3-step process. What is it? Well, extraction. That is when you're removing DNA from the nucleus of the cell. How do you do it? Well, you actually use chemicals to separate it. Amplification, this is when you are making copies of DNA in order to get a large enough sample of the same DNA sequences to work with. And how do you do it? You run the PCR, which is heating and cooling up the samples to cause them to copy from 1 to 2, 2 to 4, 4 to 8, and so on until you reach about 1 billion copies, which is what all of you did. And visualization. This is being able to see your DNA move through gel to make observations. And how do you do it? You use the, what happened? There it is. Use gel electrophoresis. So that's when you insert your DNA into the gel. You plug in, turn the power on your gel electrophoresis tray. Gene. And your DNA moves from the negative end towards the positive end, because your DNA is slightly negative. So it's going to go towards the positive, just like if you'd have a magnet and you have a positive and a negative, and they're going to attract. So the DNA is attracted to that positive end. And that's why you had to have the power on in order for it to move through the gel. Otherwise, it would just stay in those little wells where you put them in. All right, pathogenic. Remember, we cut that one out. So you don't need to have that. Just cut it out. Okay, how many copies of one original piece of DNA would you have after 6 cycles of PCR? We can figure that out, right? So 1 becomes 2, 2 becomes 4, 4 becomes 8. So now we're at 3 cycles. 8 becomes 16. 16 becomes 32. We're at 4 cycles. Now we're at 5 cycles. So now we're at our 6th cycle. 64. So there's your answer. You would have 64 in just 6 cycles. You go from 1 to 64. Yeah. All right. And now our very last one, looking at evidence in biotechnology. So within this, I'm gonna provide for you this gel. I will have it labeled already. So you're gonna have the DNA ladder, suspect A, suspect B, control H, control D. You do need to realize what this means, okay? So make sure that you include, you're not going to include the picture and drawing because I've got that there. You don't have to worry about the labels. I have that there. I'm really going to it's about writing a paragraph to describe these results. And what patterns or trends do you notice? And then if you make the claim, who took her? So who do you think took her? A suspect A or suspect B, or is it unknown? So now how does the evidence in this gel support the claim? Okay. Keep in mind what I showed you about Missy Baker. I'll go to that now. So for Missy Baker, you had two samples, right? Tube A and B. A was from suspect A, B was from suspect B. You also had control H and D. A control H came from a healthy gene, and control D came from one with a deletion mutation. And what does that mean exactly? This is all the stuff that we put in there. I'm not going to be so concerned about this. Move through it. This is that PCR process that I showed you in class, but we're going to go to this. Oh, this is a good reminder, though. Remember, I talked about how it goes from the negative end to the positive. And so you've got to turn that on to make sure it's running from this end to that through the gel electrophoresis. You can remember also on how it moves through there of that sample I showed you of the ink moving through the paper and how it moved, whoop, straight up the paper. So Missy Baker has a deletion mutation. So this gene, in this example, this is its length, okay? The CFTR gene. And that's what your genes look like in all likelihood. This deletion mutation, incredibly rare. So the gene normally looks like this, but there's a segment that is missing, which means it's gone. And now the gene looks like that. And so you can see in comparison to size, this is a much shorter gene than this one. And so when it goes through the gel, because it's smaller, do you think it's going to be easier to move through that jello? Yes. And so if it's easier to move through the jello because it's smaller, it's going to move faster through it. And if it moves faster through it, it's going to show up, it's going to move at a faster rate than someone who had a healthy gene would. So let's go back to our example. So now you can see the gel, and you can see that here's our DNA ladder. And just a reminder, this DNA ladder is made up of is not one type of DNA, it is a whole bunch of different lengths of DNA. And so it's literally this ladder of these different lengths. So can you tell me, are you going to have the shortest size DNA at the bottom coming away from the well, or are you going to have the shortest one at the top? Well, the shortest DNA is at the bottom. So all these different lengths start out here. It's like a little race, but the shortest ones move faster. And so this enables us to see and to compare how fast they move through this gel with our suspects and our controls. And it also gives us a way to measure, but we didn't get into that so much this year. So the shortest ones are down here. You can see that it's not the shortest gene because the even shorter ones are over here, but it's a shorter gene and it matches the size of that gene for the deletion mutation. So suspect B happens to have some evidence in the car of someone who would have a deletion mutation. Does that mean that suspect B has Missy Baker? Maybe, maybe not. It's strong evidence, but we're never absolute here, right? It means that the police are definitely going to be investigating suspect B further. Does suspect A have evidence of someone with a deletion mutation? No. And so suspect A is off the hook. They only have samples of DNA from their car that shows healthy genes. So it would not be logical to continue to interview and inspect suspect A. Okay? So you're telling me about how B matches the control D, how A matches with H, and including that in your reasoning. All right, and this one, as I said in class, is definitely on the final. You're going to give me a claim. You're going to write a paragraph about the reasoning, which is really this. You don't have to draw these pictures. And you're going to give me, you're going to write in the claim, you're going to write a paragraph describing the way these things match up, just like you did in your data days. And then you're going to write a paragraph on the reasoning on how you know this. All right? That is it. Happy studying, and I will see you in class for the final.